What do railroads and highways, electrical wires, leaf veins, or our own veins and arteries have in common? They all make up transport networks, moving information and resources quickly and efficiently through a system. These networks are everywhere you look. For example, in your local damp, dark forest, growing on tree bark, you might see a yellow mass, feeding, growing in a network-like pattern. This is Physarum polycephalum, also known as slime mold, even though it is not mold at all. It is actually a protist, made up of a single cell with multiple nuclei. This little being is fascinating and has been heavily studied in the last few decades. But why, you might ask? As it grows and explores its surroundings, Physarum expands its network. At first, it expands radially, in an almost uniform way. However, as it explores more space, its network adapts. Useless veins that were there before disappear, and more central veins become larger and thicker. Adaptation is the name of the game for slime mold. And this leads to extraordinary behavior. This blob shows intelligent behavior, even though it has no nervous system, no brain. It can solve mazes, it has memory, it can create networks with comparable efficiency, fault tolerance, and cost to man-made networks, like the Tokyo railroad system. This is high-level behavior with no centralized control. How is this behavior even possible? Well, it all relates to the way information is transported in slime mold. The way the network flows controls the slime mold's behavior. Physarum shows two important periodic processes that must be at the bottom of this. Peristalsis, which is a wave of contractions of the veins, and shuttle streaming, which is the back and forth motion of fluid through the veins. If we are able to model the flow of fluid inside the veins, we can understand how it works. We might even understand how to make more efficient, robust, and cheap networks. We might even understand how information is processed, how decision-making takes place. And this knowledge will not only impact how we view slime mold, but also how we view all other transport networks. For example, it can even impact how we perceive tumor irrigation and cancer development. However, how does one model this behavior? Well, using two powerful tools, graphs and hydrodynamics. The graphs describe the network itself, the connections, and the hydrodynamical equations describe the flow, the transport within it. Physarum's fluid and blood, for example, can both be described by an approximation of the Navier-Stokes equations, the Hagen-Poiseuille law. This is where my master's thesis comes in. Applications to biological networks of adaptive Hagen-Poiseuille flow on graphs. With the supervision of Professor Dilão, I intend to dive into these networks and use both new and old formalisms to study and model real biological transport network behavior. More specifically, I want to analyze networks with time-dependent sources. I want to analyze phase transitions on graph structures. I want to model Physarum's periodic behavior. I want to test old models using new results. And I want to model realistic veins that cannot stretch infinitely.